Hello, in this video I'd like to talk about types of chemical reactions as described in chapter 8.2 in your textbook. In this section of this unit, you are going to learn a very specific skill, and that skill is as follows. Look at a chemical equation and place the reaction it represents into one or more of 6 major separate categories. In other words, you are going to learn how to classify a chemical reaction. That is, tell me what type of chemical reaction it is. The immediate question is, why? Well, this is just kind of something scientists do. We like to put things in boxes, whether it's species of animals or types of minerals. We like to put them into categories based on common characteristics. And there are a couple of reasons why we like to do this. In terms of chemistry, one reason is if we know what category the chemical reaction belongs to, we understand the reaction in greater depth. If we know what characteristics that particular type of reaction has, then we feel like we understand what's going on in greater detail. Another important reason why is because if we know what category it belongs to, it allows us to predict the outcome, that is the products of the reaction. So you will see later in this video that there are certain categories of reactions for which, if I specify the reactants, you can tell me what category it belongs to, and then based on that, you can tell me what the outcome of the chemical reaction is. So here's how this is going to work. On the next 5 slides, I will give you a series of chemical equations representing chemical reactions. I would like you to look at those equations and see if you can tell me what they all have in common. What characteristics does each example on each slide have in common? And then we'll talk about what category that belongs to. So let's begin. Gallium reacts with chlorine to form gallium chloride. Phosphorus reacts with fluorine to form phosphorus pentafluoride. Magnesium oxide reacts with carbon dioxide to form magnesium carbonate. What do all of these reactions have in common? If you'd like to pause the video and think about this for a few minutes, go right ahead. What you will see is that in each of these reactions, 2 simpler reactants combine to form a single, more complex product, which is a chemical compound. The reactants can be elements, they can be compounds, but in each case, we have 2 reactants coming together to form a single compound. Each of these is an example of what is called a synthesis reaction. And the definition of a synthesis reaction is one in which 2 or more simpler substances combine to form a single new compound. We could symbolically represent a synthesis reaction using the generic formulation A plus X forms AX, indicating 2 reactants that are different from each other form a single new compound. So if you see that your reaction follows this general pattern, you will say it is a synthesis reaction. For our next category, barium hydroxide forms barium oxide plus water. Chromium-3 bromide forms chromium plus bromine. Aluminum sulfate forms aluminum oxide plus sulfur trioxide. What do all these reactions have in common? Well, as you can see in each of these reactions, a single, more complex compound is breaking down or splitting apart to form 2 or more simpler substances. The products can either be compounds or elements, but in each case, a single reactant forms 2 simpler things. Obviously, this is simply the reverse of what we saw in the previous slide. These are called decomposition reactions. And in a decomposition reaction, a single compound breaks down to form 2 or more simpler substances. And we could symbolically represent the decomposition reaction with the reverse of the synthesis, which is AX forms A plus X. In our next category, lead-2 nitrate reacts with zinc to form lead plus zinc-2 nitrate. Cobalt-3 sulfide reacts with oxygen to form cobalt plus sulfur dioxide. Potassium iodide reacts with bromine to form iodine plus potassium bromide. What do all these reactions have in common? Well, as you can see, in each reaction, we have 2 reactant formulas and 2 product formulas. And we see in each reaction, a compound reacts with a pure element to form a different pure element and a different compound. And in fact, what you can see is that the element seems to be displacing the element from the compound. So for example, in the first reaction, zinc is displacing lead from lead to nitrate. Lead goes off by itself, and zinc combines with nitrate. Likewise, in the second example, oxygen reacts with cobalt-3 sulfide, kicking out the cobalt. Cobalt goes off by itself, and now oxygen is combined with sulfur. Each of these is an example of what's called a single displacement reaction, in which one element displaces another in a compound, forming a new compound. Single displacement reactions always have the generic formula compound plus pure element forms a different pure element plus a different compound. And as such, I could write a symbolic representation for it that looks like AX plus B forms A plus BX. Notice that each of these reactions involves a pure element, which will become important later. For our fourth category, silver 1 nitrate reacts with potassium bromide to form silver 1 bromide plus potassium nitrate. Iron 3 sulfate reacts with sodium carbonate to form iron 3 carbonate plus sodium sulfate. Sodium hydroxide plus hydrochloric acid forms hydrogen hydroxide plus sodium chloride. What do all these reactions have in common? Well, as you can see, in each of these reactions, we are combining two ionic compounds to form two new ionic compounds in which the ions seem to have simply traded partners. So for example, in the first reaction, silver 1 nitrate reacts with potassium bromide. The silver 1 cations combine with the bromide anions, and the potassium cations combine with the nitrate anions to form silver 1 bromide and potassium nitrate. And the same pattern occurs for each of these examples. Each of these is an example of what's called a double displacement reaction in which two ionic compounds exchange ions. And I can write a symbolic representation for that as AX plus BY forms AY plus BX. In our fifth category, ethane reacts with oxygen to form carbon dioxide plus water. Copper reacts with oxygen to form copper 1 oxide. Ammonia reacts with oxygen to form nitrogen monoxide and water vapor. What do all these reactions have in common? Well, as you can see in each of these reactions, a substance, a compound or an element, is combining with elemental oxygen, O2 gas, to form products, each of which contains oxygen. Each of these is an example of what's called a combustion reaction. And the definition of a combustion reaction is when a substance combines with O2 forming oxygenated products. So whenever a substance, a compound or an element, combines with O2 and every product formed, no matter how many there are, contains O, then that's a combustion reaction. And we can symbolize that as X plus O2 reacts to form XO. So, let's summarize. In a synthesis reaction, A plus X forms AX. In a decomposition reaction, the reverse of synthesis, AX forms A plus X. In a single displacement reaction, AX combines with B. B displaces A to form A plus BX. In a double displacement reaction, AX reacts with BY, exchanging partners to form AY plus BX. And in a combustion reaction, some substance combines with O2 to form products that contain oxygen. So here's an interesting question. Could a reaction fall into more than one category? If so, what are those categories? Well, if you glance back, let's go back a couple of slides, and here in my second example, I see what is clearly a combustion reaction by our definition, but it also involves two elements combining to form a single product. What category does that also belong to? You're right, it's a synthesis reaction. So it can be, if it is a synthesis reaction with O2 as a reactant, okay, and all products contain oxygen, then we can say that this reaction is also combustion. So here's an example where two of the categories we learned about, synthesis and combustion, can overlap if O2 is one of the reactants. However, there is another category that we learned about. What did we just spend a lot of time talking about? And that is oxidation reduction reactions. What's an oxidation reduction reaction? One in which there is transfer of electrons as shown by change in oxidation number. So, of the 5 categories we just learned about, which of these are always oxidation reduction, never oxidation reduction, or sometimes oxidation reduction? Well, let's go back and look. Clearly, combustion, in which we combine something with O2, is an oxidation reduction reaction. That was our earliest definition of oxidation, combining with oxygen to form oxygenated products. Now notice also that in this reaction, oxygen starts with an oxidation number of 0 and ends up with an oxidation number of -2. Well, that kind of implies that any reaction that contains a pure element on either side must be an oxidation reduction reaction, because if it contains a pure element on one side of the arrow, in which the oxidation number is 0, on the other side of the arrow, the oxidation number must be not 0. So it's changing. So we can conclude that the reactions that are always redox would include combustion and single displacement. Because if we look back at our single displacement reactions, which are right here, we will see that single displacement always involves a pure element on both the reactant and the product side. Are any of these reactions never oxidation reduction? Well, if you go back and look at our double displacement reactions, in which two ionic compounds exchange ions, all we're doing is trading partners. No one is gaining or losing electrons. So double displacement would be never redox. Which are sometimes redox? Well, again, using the general idea that if a chemical reaction involves a pure element on either the reactant or product side, we can go back and see that our synthesis and decomposition reactions are sometimes redox, because in these cases we can see that some of these reactions involve pure elements, but the third one does not. Here, likewise, some of these involve pure elements, but others do not. So, to complete our summary, we can say that those that are sometimes redox include synthesis and decomposition. So if a synthesis or decomposition reaction has a pure element on either side, then we would conclude that it is also redox. But if it doesn't involve a pure element on either side, then we need to assign oxidation numbers to determine whether it's oxidation reduction or not. Now, our final topic is, for which categories of reactions can you predict the outcome? There are 2 types of reactions for which I expect you to be able to tell me what the products are if all I give you are the reactants. So let's talk about these. The first is synthesis of an ionic compound from a metal and a nonmetal. This is something you've done before. If, based on its location in the periodic table, you can tell me the charge on the cation the metal will form, then you can predict the formula of the product from which you can balance the equation. So for example, potassium is heated in the presence of sulfur. Potassium is a monatomic solid. Sulfur occurs as molecules of S8. All of that should be in your notes, by the way. We know that a metal and a nonmetal react to form an ionic compound. So by simply writing the symbols of the ions formed by potassium and sulfur, we can predict the formula of the ionic compound they produce. Potassium forms a cation with a single positive charge. Sulfur forms an anion with a 2 negative charge. That allows me to write the formula K2S. And we also have in our notes that pure ionic compounds are always solid. To balance the equation, I'll put an 8 before the potassium sulfide and a 16 before the potassium. The other example of a reaction for which you can predict the outcome is one that you haven't encountered before, but I'm telling you about it now, and that is combustion of a compound that contains carbon and hydrogen. Anytime you burn something that contains carbon and hydrogen, you always get the same two products. Carbon and hydrogen end up in their most oxidized form. Let's see what that is. So, liquid ethanol is burned in air. If you've ever lit an alcohol burner, then you know what this looks like. Liquid ethanol has the formula C2H6O. If I burn it in air, it is combining with O2 gas. This needs to be in your notes. When you combust something that contains carbon and hydrogen, all of the carbon forms the most oxidized form of carbon, which is carbon dioxide gas. All of the hydrogen forms the most oxidized form of hydrogen, which is water. And whether it's water in the gas or liquid form depends on the temperature, so it doesn't matter. Either one is fine, but those are the two products. To balance the equation, I'm going to put a 2 before the carbon dioxide to balance carbon. I'm going to put a 3 before the water to balance hydrogen. That gives me a total of 4 plus 3, or 7 oxygen atoms on the product side. Of those 7, 1 on the reactant side is part of ethanol. 7 minus 1 is 6, so that means I need 3 oxygen atoms to balance the equation. So let's put the entire unit together. This is everything that we've covered from Chapter 8. So I give you a verbal description of a chemical reaction, and you write a balanced chemical equation to represent the reaction, predicting products in some cases, in the 2 cases we just talked about. Tell me which category or categories it belongs to, and if it's an oxidation-reduction reaction, identify the element being oxidized, the element being reduced, identify the oxidizing agent and the reducing agent. And on the last slide, let's do an example of this. So here's my verbal description. Iron reacts with nitric acid to form hydrogen and a solution of iron 3 nitrate. Iron is a monatomic solid. I look up the formula of nitric acid on my nomenclature sheet and I see it as HNO3, and acids are always aqueous. Hydrogen, I know from my notes, is a diatomic gas. Iron 3 nitrate, iron 3 means iron with a 3 plus charge. Nitrate from my nomenclature sheet has the formula NO3 minus, so I'll write the formula FeNO3, and because I'm told it's a solution of iron 3 nitrate, I will indicate the physical state as aqueous. Okay. So that's step 1. I have all the formulas and I have the correct physical states. So now let's balance the equation. To balance nitrate, which I'll treat as a unit, I've got 3 nitrates on the product side, so I will put a 3 before nitric acid to give me 3 nitrates. That gives me 3 hydrogen atoms on the reactant side, 2 on the product side. So to balance hydrogens, I'm going to need a temporary fractional coefficient of 3 halves. At this point, iron, hydrogen, and nitrate are balanced, but I don't have integer coefficients, so I have to fix it. To make the coefficients all integers, I will multiply everything by 2. And to make my life easier, I'm simply going to erase what I've written here and replace them with the coefficients multiplied by 2. So iron takes a coefficient of 2. Hydrogen becomes 6. Nitric acid becomes 6. Hydrogen becomes 3. And iron 3 nitrate becomes 2. So there is my balanced equation. So now I'm going to we're going to determine what category or categories it belongs to. I have iron, a pure element, reacting with a compound, nitric acid, to form hydrogen, a different pure element, and iron 3 nitrate, a compound. Anytime I have an element plus a compound reacting to form a different element and a different compound, that belongs to single displacement. And because single displacement always involves a pure element on either side of the equation, it is also oxidation, reduction, or redox. The fact that it's redox means now I need to assign oxidation numbers and identify which element is being oxidized and which is being reduced. So iron and hydrogen as pure elements have oxidation numbers of 0. In iron 3 nitrate, iron has an oxidation number of +3. It's a monatomic cation, and the oxidation number is the same as the charge, so that's +3. Hydrogen in nitric acid is part of a compound. It has an oxidation number of +1. To determine the oxidation number of nitrogen and nitric acid, I need to use the fact that the sum of the oxidation numbers of every atom in the formula is equal to the overall charge in the formula, which in this case is 0. Each of the 3 oxygens has an oxidation number of -2. 3 times -2 is -6. Plus 1 is -5. In order for the charge, the oxidation numbers to add to 0, nitrogen must have an oxidation number of +5. In iron 3 nitrate, I'm just going to look at the nitrogen as part of nitrate. Each of the 3 oxygen atoms has an oxidation number of -2. In order for the sum of the oxidation numbers of all the atoms in the nitrate anion to equal the charge, which is -1, nitrogen must have an oxidation number of +5. So, to determine which element is oxidized and which is reduced, I will simply look at change in oxidation numbers. So, iron is oxidized because its oxidation number goes from 0 to +3. Hydrogen is reduced because its oxidation number goes from +1 in nitric acid to 0 in elemental hydrogen. If iron is being oxidized, then nitric acid must be the oxidizing agent, and that's because it contains hydrogen, which is the element being reduced. Hydrogen is being reduced, so iron must be the reducing agent, again because it contains iron, the element being oxidized. And that's pretty much it for this unit.